Welcome everyone to section number 7. This is maximums and minimum values here for multivariable functions, right? And the claim is I have a very boring video for you, but that's okay. We can get all the boring stuff done before class so that way we can do a few more examples and the exciting stuff, in person. So this is going to be definitions and a bit of a history lesson. We want to think back to the world of Math 132, that's Calc 1. And we're going to go ahead and think about ways to find maximums and minimums in this section. So, like it says here, we're going to be kind of restricting ourselves down, and we're only going to be using 2 variables in this section. We're not going to learn how to minimize or maximize 3 variable functions. It's just going to be, functions of x's and y's. That's how we're going to finish up this chapter here. All right, so quite a few definitions. The first one, we have a function of 2 variables has a local maximum at a point AB if it's the biggest thing around, right? So f of AB is bigger than or equal to any other xy, right, where xy is near AB. Then that number, f of AB, is called the local maximum value. Local maximum value. Okay, so if you asked what is the local maximum, or what's the local maximum value, right, you would specify f of AB, whatever that value is. Maybe it's 5, maybe it's 10, whatever. But if you wanted to know where does the local maximum occur, well, that's at the point, right? So this is a point, this is a number, the actual value itself. Likewise, we can define the local minimum, and it has a definition that you would probably expect now, right? So if f of AB is the smallest thing around, right? So in this case, f of AB should be less than or equal to any f of xy, where xy is near AB, right? It's just local minimum, so anywhere near, it's the smallest thing around. Then that f of AB, right, is going to be called the local minimum value. All right, if these inequalities actually hold for all points xy in the domain of f, then f has an absolute maximum or absolute minimum at this point AB. So locals and absolute, right? Maximums and minimums. This is kind of similar to back in our Calc 1 days, right? We had local mins and maxes, and we had absolute mins and maxes. All right, so we want to upgrade, and we want to know how do we actually find these things, right? So we are going to upgrade from our Calc 1 days, and we're going to talk a little bit about maybe critical points here in just a second. Actually, we'll do a theorem first. So if f has a local maximum or minimum at this point, then the first order partial derivatives of f exist there, right? So first of all, if it has a local maximum minimum and the first order partial derivatives exist, then the claim is both of them are equal to 0 at this point. So the x partial derivative of f at the point is 0, and the y partial derivative at this point is equal to 0. So this kind of brings us back into our Calc 1 days, right, of critical points. So we're going to say a point AB is called a critical point, or in some books out there, these are also regarded as stationary points of f if either, right, so, well, if both of the first partial derivatives with respect to x and with respect to y are both 0, or, notice one of the conditions up here was that the first order partial derivatives exist. So also you may have one of these situations where maybe the derivative doesn't exist. And in that case, right, if either one of these partial derivatives don't exist, we're going to still consider this a critical point. Critical points, right, that are not local extrema, therefore local mins, local maxes, things like this, these are going to be called saddle points. And we'll see why. It's because the graph kind of looks like a saddle at these points, right? So we'll do that in class. We'll actually show some saddle points. Okay. So the claim is, right, if we have a graph in front of us, it's pretty easy to locate local mins and local maxes, right? So here's kind of our classic graph, and I would say right here and here, these 2 points, these are going to be local maxes, right? Kind of everywhere around it, it's the highest value. And likewise down here, and I know that there's another one over here, although I can barely see it, these right here are going to be local mins, or local minimums, because they're the smallest values around, right? So with a graph, it's easy. But we want to develop, similar to Calc 1 here, we want to develop a test to find local maximums and minimums just from an equation, right? Quite often we're given the equation, we're not given the graph, so I'd like to be able to find local mins and maxes just from an equation. All right, so this is the history lesson, back in Calc 1 days, right? So back in Calc 1, Math 132 here in MSU, right? Typically, everyone loved the first derivative test, right? So when we were doing Calc 1, we loved the first derivative test, which went like this. Find all the critical points, okay? We can do that. List them all on a number line, and then choose test points, right? So maybe I have a couple of them here. I'm going to say maybe 0 and 5, and we would choose test points. So we would choose something like, here's a test point -1, here's a test point in this interval 2, here's a test point over here 6, and we would test these and we'd figure out if the derivative, so this is all with respect to the derivative here, is positive or negative on each one of these intervals. So maybe it goes positive, negative, positive, something like this. So again, we choose those test points in each interval and evaluate the derivative there. See if it's positive or negative. And then we use the following rules, right? So if the derivative goes from positive to negative at this critical point, then we have a max, right? Because it would be increasing. Derivative is positive means increasing, and then the derivative is negative means decreasing. So therefore we have a max there, right? It kind of looks like a local maximum. Likewise, if the derivative goes from negative to positive, right? So negative means decreasing function, positive means increasing function, right? We'd have a minimum there. So that's this A and the B. And then if there's no change, right? If it goes from negative to negative or positive to positive, then we have neither, which we're now defining these things as saddle points. Okay, so let's think about the first derivative test, right? So if I want to use the first derivative test up here, the claim is, well, we're going to have an issue. We won't actually be able to use this in the multivariable case. And the claim is, well, because if I have a critical point, right? Before I took all my critical points and I broke up the number line. But if I have a critical point now for a multivariable function, now let's go ahead and say this is a critical point right here. Notice it doesn't break up the plane at all, right? It doesn't break up the plane, and so there's no natural places to maybe choose these test values, right? These test values, and even then, should I go over the critical point maybe from left to right, or from right to left, from top to bottom, right? It's hard to say how I need to kind of go over this critical point. Here it was very natural, right? There's only one direction to go, right? You go from left to right, and this just goes over the critical point completely. So that's the issue here with the first derivative test. So therefore, we go and we look at the second derivative test. The claim is the first derivative test, it won't work for multivariable calculus. Well, you can kind of, it's very complicated. You can kind of fix it and stuff, but it's horrible. The much easier one to use in multivariable calculus, right, is the second derivatives test, right, which I say here is everyone's second favorite out of the two. And this was a bit of a pain, right, because you had to calculate out the second derivative. It was a bit messy, but here's how it went, right? So you finally list all the critical points, check, calculate out the second derivative, and evaluate at each one of these critical points. And then the claim is, if that second derivative was less than 0, we had a local max. If that second derivative at this point was greater than 0, we had a local min. And then if it was equal to 0, the test was inconclusive and we didn't know, what was going on there. So it could be a local min, it could be a local max, it could be a saddle point. We just don't know, right? It's inconclusive. Okay, so if I want to use something like this, the claim is this is actually recoverable. We'll be able to do something like this. But if I want to use this, right, we have a lot of second derivatives, right? Which second derivative should we use? Should we use f sub xx, f sub xy, f sub yy? Remember, kind of the mixed partials are often the same. And the answer is all of them. Frowny face. So it is mildly complicated, but we'll be able to do this. We'll be able to use a second derivative test, really, to classify critical points as either minimums or maximums here for our multivariable functions. And that's where this video ends. I know it's a bit of a cliffhanger. I'm sorry to do that to you guys, but we'll talk in class about how to actually do a second derivative test for multivariable functions. All right, I'll see you then.